Right, hello everyone, and thank you for coming to the special edition of our crystallography club. Today we are hosting the talk of Dr. Owen, who was a PhD student in the laboratory of Professor Goran at Oxford University, studying radiation damage to protein crystals. He then moved to the Swiss light source, and during his postdoctoral time there, he built means to collect data orthogonal to X-ray diffraction, like UV and Raman, from protein crystals in the beamline, so that one can expand ways to study, for example, proteins with cofactor or metal enzymes. And that is also where he collaborated with my former lab on a number of very important structures.
Goran told me they were important.
So at present, Robin is at the diamond light source in England, which is one of the world's most powerful and youngest synchrotrons. Working as a principal beamline scientist. Robin, thanks for coming. We are excited to hear your talk.
Okay, great, thanks. Okay, so yes, first thanks to Goran for the invitation to come and speak. And yeah, so what I'm going to talk about tell you about some of the things that we're doing at Diamond. Hopefully find some of them interesting, and hopefully maybe you can feel like you'd like to come to Diamond as well and try some of them out, or they kind of inform what you do to collect data as well. So I guess the first thing to say is, where is Diamond? So Diamond's in the south of England, so you have London here, and then Oxford up here somewhere, and then Diamond's just in the countryside to the south of Oxford. So about, 20 miles south of Oxford or something. And so we're on, even though we're in the countryside, there's quite a few things around us. We're on one of the UK's national science campuses. So we've got ISIS here, which is a neutron source. We've got the Central Laser Facility, and then we've got several labs for the European Space Agency as well. But I guess the most imposing thing, certainly from an aerial point of view, is Diamond, which is here. So if you have a look within Diamond, what do we have? So this is purely just the MX village. So we have 5 different beamlines dedicated to macromolecular crystallography. And the idea is that while we can all you can collect very good data at all the beamlines, we're kind of a quite a close-knit group that we've worked together. And the idea is maybe that each of the beamlines kind of does something slightly different to all the other beamlines. So for example, IO3, you can collect category 3, data from category 3 samples, so samples that require a higher biocontainment level. IO4 specialises in kappa goniometry, and I24, which is my beamline, is dedicated to tunable microfocus. So even though, as Goran mentioned, we're kind of one of the younger synchrotrons around, one of the newer synchrotrons, we're still changing quite a lot and removing beamlines and introducing new beamlines within the MX village. So over the next couple of years, there'll be 2 new beamlines come online. And the first one of those will be I23, which will hopefully be online later this year, which is dedicated to long wavelength MX, so for phasing, native phasing of proteins. So that will hopefully come online, towards the end of this year. And then also what is progressing at the moment is IO2 will split into 2 beamlines, one dedicated to in situ MX and one dedicated to microfocus. So microfocus is kind of really the main topic of the talk really today. So at Diamond, there's two means of achieving microfocus beams. So there's IO4. So IO4 use CRLs to achieve a microfocus beam. So that has the advantage that it's relatively easy to get very small beams. You can get an 8 by 2 micron beam but at the price that the beam size changes as a function of energy. And then also the flux is slightly reduced. But what I'll talk about today and throughout the rest of the talk is my beamline, so Beamline I-24. So on I-24 we use mirrors, a two-stage demagnification to achieve a micro beam, and what advantage that has is you can have a continually variable beam size, and that beam size doesn't change at all over the full energy range. So you can just choose a beam size and then dial up your energy essentially. And got relatively high flux as well, so very high flux density into a small area. And then we're also equipped with a Pilatus 3 pixel detector, which I'll talk about a little bit more. So yeah, so the Pilatus 3 6M detector, so that's the second generation of commercial Pilatus detectors, and so that's capable of collecting up to 100 frames per second. And that's something that's become, so we've had it on the Beamline now for, I guess, a year and a half, maybe, 18 months. And over the last year or so, something that's become routine is that users will come and collect data at 100 hertz. That's starting to become the norm now. And yeah, several advantages of the detector: low noise, high dynamic range, and very small readout time. The other thing that we can do on I-24 is in situ experiments. And what we mean by in situ is we have a special bracket so we can mount the crystallization tray directly in the X-ray beam. And the in situ approach has several advantages. So, really, I think the first one that we kind of came to was that when you're mounting very small crystals, it can be quite difficult to remove them from the drop, so fish them from the drop. So you can damage the crystals doing that, and you can also damage the crystals when you're trying to cryoprotect them or cryo-cool them. And what in situ does is it allows you to start to deconvolute those two effects from the initial quality of the crystals. And this is quite a nice illustration of this from Isabel in the membrane protein laboratory, which is based within Diamond. And so these are two crystals from the same crystallization condition. And so this is data collected directly. You can't see so well on the display, maybe. But so from data collected from the crystal in the drop, extended to around about 10 angstroms, was data collected from the crystal, looped up and mounted at 100 Kelvin, only went to about 30, 35 angstroms. So there's quite a difference. So you're starting to deconvolute the effects of how well you can loop up crystals and how good your cryoprotection is from what the initial quality of the crystal is. And then the second aspect of in situ data collection is that we didn't want to just be stuck at this screening step. So there's several proteins, and I guess the obvious one is viruses that really they prove to be impossible to cryo-cool. And that's really particularly true for viruses. So the example here is foot and mouth disease virus, solved by Dave Stewart and workers from his group. And what you can see here is it's of two mutants. So you have the wild type form here with histidine residues. So they mutated these to cysteine and formed a bond between two different subunits of the capsid. And what they found was that really stabilized the capsid, the formation of the disulfide bond. And determining the structure helped to understand why that was so effective. And this approach has really proved to be quite successful. So I think now we're up to about 14 or 15 icosahedral structures, virus structures solved at the Beamline, and I think that's almost 5% of the total number of icosahedral viruses in the protein data bank. So it's really been quite successful. But there's a caveat, there's always a catch. So the catch really comes back to the reason why we cryo-cool data. So why we cryo-cool crystals, sorry. And yeah, we cryo-cool crystals to mitigate radiation damage, right? So you cool them and you can actually collect complete data sets. And as you can see, at room temperature, where you don't cryo-cool, the effects of the beam can be quite dramatic and really quite fast. So as part of my research, I wanted to try and answer some questions about this, and they were, how can we maximise the amount of data that we can collect at room temperature? And maybe can we start to think about outrunning radiation damage? Can we collect data before the damage kicks in? So in order to do that, we wanted to collect data even faster, so faster than the 100 Hertz that I mentioned. There we go. Okay, so for that we borrowed a detector from Detectors. So this is a Pilatus 3 300K. So this was capable of collecting data up to 500 Hertz. So 2 millisecond images. So before we started looking into crystal lifetimes and so on, the first question that we wanted to answer was, can we collect data at 500 Hertz? Or can we collect good data at 500 Hertz? Okay, so this is a 1 millisecond image collected at I24. So you can see even with 1 millisecond, the flux density at I24 is so high I can really collect very good data. So I think this isn't I think this data as well. This was even with the beam attenuated. So this is 40% transmission and a 1 millisecond image. So yeah, quite impressive. Okay, so if you start to look at the stats for that, admittedly it's lysozyme, but you have to start somewhere when you're kind of benchmarking detectors and things. So yeah, as I mentioned, so it's 2 milliseconds. Of that, just under half is readout. So it's the detector's live, if you like, for 1 millisecond. And for our initial data set, then for a first data set, the stats weren't too bad. Actually. So if you have a look at what data collection actually looks like when you start collecting that fast, you see the scatterguard moves up into the beam. Goniometer winds up, ready to get ready, and you'll see there's a scintillator at the end of the beam stop here that comes on when the X-ray shutter opens. So, yeah, X-ray shutter opens, X-ray shutter closes, and that's a complete data set done. So, yeah, it starts to change the way you think about collecting data and how long data collections take, and how much data it's possible to collect. So, what did we find when we started looking at crystal lifetimes? So, there were two main findings. Really. So, at 100 Kelvin, it doesn't really matter how you collect the data. If you collect at 100% transmission and don't attenuate the beam, you can collect the same amount of data as if you collected 10% for 10 times longer. There's no dose rate effect at 100 Kelvin. What we found at room temperature is that by collecting faster, we can partially outrun radiation damage. So by collecting data, so you see here the dose rate increases as we go this way. As we increase the dose rate, then the lifetime also increases. So by collecting faster with more intense beam, we can collect more data, so we can start to outrun damage. So, and then the next thing that I won't go into detail in today is that we also found that there's a lag phase in the intensity decay. So we see a two-phase decay. So we see an initial slow decay, and then that's followed by a rapid exponential like decay. So look into the future, what we want to do is try and collect faster and then try and exploit these two effects to collect significantly more data from room temperature crystals. And that will start to then circumvent some of the challenges associated with room temperature crystallography. So, merging data from many tens of crystals. So it becomes a much more, it's not an insurmountable challenge at all, but it becomes definitely an easier challenge if you, for example, have to merge data from 10 crystals instead of 70 crystals. Things become a little bit easier. Okay, so moving on a little bit back to the title of the talk. So we talked a little bit about faster, certainly in relation to room temperature data collection. So let's highlight what we're doing in terms of collecting data from smaller and smaller crystals. So the first lesson of microcrystallography is that easy things start to become hard. So the things that you kind of took for granted when you are mounting your kind of 100 micron crystals or 50 micron crystals, they start to become really difficult. So crystals become difficult to see, especially, I guess the classic example is if you're collecting stuff that's been grown in LCP, when you then cryocool the LCP, it becomes opaque, you can't then see the crystals, so you have to be able to deal with that. Refraction becomes a really big problem with very small crystals. And then also, when you start collecting data from microcrystals, you start to move away from the idea of having one pin, one crystal. Instead, you might have one pin with a mesh with 10, 20 crystals on. So then kind of starting to try and think of methods to how do you quickly find where these 10 crystals are, where these 20 crystals are. How do you quickly select what the best ones are? And then also, I guess an important point is that Microfocus MX isn't just, we're not just looking for small crystals, we're also looking at subvolumes of larger crystals. So crystals can be quite inhomogeneous. And I guess the key premise of Microfocus MX is background and signal to noise. So the entire premise is that you're reducing background. And that's kind of shown schematically here, I guess. So in this case, everything kind of looks good, but then we start to have a problem when the crystal size shrinks down. So in this case, then the background then starts to become comparable to the signal from the crystal, if you like. And the way in which to bring that back and collect good data from the crystal is to reduce the beam size. So in the, well, I guess in the kind of simple example on the slide, it's shown as slits, but what we do on I-24 is we're not reducing the flux of the sample, we're using the mirrors to focus the beam down to this 8x8. So we're not reducing the beam size at the expense of flux, we're just achieving a smaller beam size. So to illustrate how much of an effect that would have, we collected data from some polyhedra crystals. So I think these are about 4x4x4 microns. You can see, well, you can't really see, but they tended to collect in the corners of these 25 micron meshes. So there's one there, and I guess you just have to take my word for it. But yeah, so we collected data from we collected data at one point with two different beam sizes, is what I meant to say. Yeah, 8 micron beam and a 5 micron beam. So, and what we did is we adjusted the exposure time for the 5 micron beam so that the integrated intensity in each spot was around about the same. And this kind of comes back and just reinforces the message that what you're doing is you're collecting less noise, if you like. If you like, the photons that you're shining on the sample are kind of obvious, they're kind of being usefully used. So instead, even though we had a 14-fold decrease in flux, we only did three times longer increase in exposure to get the same intensity. And if we look more qualitatively, compare the diffraction images, it becomes more striking when you can just visually see the difference in the background. And I guess the key point, if it was your data collection, was with the larger beam, got I of sigma I of 1.5 and 2.9 angstroms in comparison to 2.5 angstroms with the smaller beam. So it starts to make a big difference in what you can get from the same crystal. Okay, so mentioned also using the microbeam to look at small subvolumes of larger crystals. So these are crystals of A2A receptor from SOA Waters lab. So they collected data from this on two beamlines. One, if you like, normal for the sake of nomenclature, with a beam size of 70 by 70 microns, and then also an I-24 with 10 by 10. And again, sorry, the diffraction patterns don't tend to show up so well on JPEGs. So with the normal beam size, what they found was diffractions around 2.7 angstroms, with the micro beam 2.5. So you're kind of cutting out regions that don't usefully contribute to the diffraction pattern, if you like. And then to give just to kind of quantify a little bit more, here's an example of another crystal. Sorry. mounted at the beamline, and this kind of highlights the kind of I mentioned the difficulty in finding crystals and finding small crystals on meshes. So we have a tool at the beamline called grid scan, and what that does is it moves the sample continuously through the beam, and so you can analyse large areas very quickly. So these 360 images can be collected in 150 seconds. And I guess the thing I would highlight is this slide's actually quite old. So this was with the old detector. Now we can collect at 100 hertz, so 100 frames per second. So we can raster over a grid this size in 20, 30 seconds. And I think maybe what's more useful to you is instead of having to look through 360 images, all the images are automatically scored for you. And the same goes for when you collect data. When you collect the data set, it's automatically integrated for you, and you're given all the stats. So when you're trying to collect maybe 20, 30 data sets per hour, then that automatic processing kind of keeps up with data collection and allows you to kind of continuously evaluate where you are. And there's different ways of representing the results as well. So you can have blobs, you can have contour maps, and they kind of give a nice idea for where the best regions of the crystal are. So to illustrate how much of an effect it can have even within a crystal, so you collect data at different points. You can see the difference starts to be quite large, so from 3.4 to 2.6 angstrom, quite a large variation, even just over one crystal. Another option that we have at I-24, well, in fact all the diamond beam lines, is line scan, so that's collecting, if you like, in a helix through the crystal, so continually translating the crystal during data collection. So collected data between 2 points on the other region of the crystal, but we didn't collect those wedges, and then that was even to a slightly better resolution. So that really just illustrates the effect of continually introducing new material into the beam and minimising radiation damage. So just to summarise really quickly. So I guess the main lessons are really when you start moving to very small crystals, certainly less than 5 microns, easy things start to become difficult. And I think probably the main lesson is that you really need to be prepared to spend more time per crystal. And it's really by kind of playing with the small details and taking the time per crystal that you can really get the best data from very small crystals. I've got a couple of examples, and hopefully try and point out some of the ways in which some of our users collected data that can kind of show what it's possible to achieve. So with this example and the next couple of examples, I guess the thing I would stress, and I've already stressed it to Goran as well, is don't ask me about what GPCRs do or any biology. That's kind of not my area of expertise at all. So I kind of involved on the data collection side and data processing side of things. So this is Class B GPCR from Casper and Andy are the guys working on the diffraction side of things. And in fact, this is something that's been quite successful. So you might have seen, I think about 3 weeks ago, Heptara had another GPCR structure, the first Class C GPCR. And that's kind of using exactly the same methods that proved successful with this. So Heptara's really been very successful collecting data at I-24, and I think because they've really kind of worked on optimizing the data collection protocols, and that kind of even starts when they're crystallizing their protein. So at some point they determine that crystals 15 to 20 microns in size, that's sufficient. You don't need to optimize further. That's enough. You don't need crystals bigger than that. So here we are, we've got the crystals 15 to 20 microns in size, grown in LCP. So again, we run into the problem when it's cooled, it becomes invisible. So again, now start to exploiting the tools available on the Beamline. So grid scan over the entire loop with attenuated beam locates the crystals. If they've got smaller crystals, you can reduce the beam size and raster again on the region of interest, and then collect a wedge of data. So in terms of data collection protocols and data processing protocols, I think the pathway they followed, I think kind of one of the important points is the second box here. So what they did is they really determined, had a good idea of what the lifetime of the crystals was in the beam. And I think, especially for very small crystals, you move away from the idea of collecting a complete data set. You're not going to get a complete data set from the crystal. So at some point they're happy that they can collect data to about 3 angstroms, but only 2 to 3 degrees. So the data collection protocol is to collect many wedges of small data, and then to build up a complete data set from using this micro diffraction assembly method. So there's a nice description in the Hansen paper, actually. But in brief, what you do is you split the data up into 1 degree bins and then scale it against the reference data set. And then you kind of iteratively find what the good wedges of data are and kind of merge them into your data set until you end up with a final data set. And then the electron density actually looked very good. So second example, so this is in cellular data structure determination. So this is quite a nice example because it's quite small crystals, but this is collecting data from crystals that were growing within the cell. So the crystals remain in a biologically relevant environment. Time and effort for sample prep is reduced, and then also so you remove this step of having to try and get the crystals out as well. But I think kind of the key thing that Jeff and Goran really had a lot of success with at the start was really optimizing the sample mounting. So you can see in this example, you've got the mylar mesh. The mylar mesh is thicker than the amount of solvent that they've got around the crystals. So really optimizing that really made the difference. So you can see, just about see the crystals. Just about see the crystals here. And again, matching the beam size to the crystals. So reducing the beam size down to 6 by 6 increases the resolution of the data they can get from 2.2 to 1.7. So kind of saying the same thing again and again, but it's having a big impact on what you can collect. In terms of data processing, so this is quite nice. So this is exploiting the automatic data processing of Diamond. So they collected data from 40 crystals. 20 crystals integrated automatically and then merged automatically into blend. So it's not a bad data set. Just to highlight that failure generally, either the data sets were blank or very weak, so poor crystals, or if the crystal happens to move in and out of the beam. And I guess you can kind of say they're kind of fortunate because it's I23, but the kind of same principles apply. It's lower symmetry, just upping the number of crystals. Yeah. And resultant electron density, really not bad at all, actually. So onto the last example. So this is LTPDE. So this is by Zhao Changdong and Neil Patterson, postdoc on the Beamline. He did a lot of the data. He did a lot of the data collection, data processing, and structure determination. So this is this highlights two or three aspects of the Beamline really. So in this case, they had relatively large crystals, so 80 microns, 80 to 100 microns, so quite large. But different challenges, so highly anisotropic diffraction. So what you can see in the plot here is, so this is the diffracting power as a function of angle. So you can see the diffracting power is going up and down as you rotate the crystal, so highly anisotropic. That's then coupled to the low symmetry of the crystals. And then with the problem, or if you like the challenge, that they're expecting mainly a beta sheet structure, so you need a decent quality map to that you can build into it. And then this was then compounded that by the fact that they had a relatively small number of crystals available. And as always with these things, they kind of had a limited amount of time left before their beam time finished. So what did we do? So we needed phasers. So it was full crystal, full wavelength MAD. So I should have mentioned, if I don't think I did. Yeah, so the anomalous scatter at selenium. So 720 degrees per energy. So with this, we kind of haven't got so small crystals, so we're increasing the beam size. So then you get a longer crystal lifetime. So that's why it's possible to collect so much data, but still cutting back the data sets to mitigate when radiation damage is obviously becoming a problem. So 55,000 frames. And I guess the real thing to point out is 55,000 frames took 17 minutes. So that's kind of quite staggering, really. And you kind of think, you know, when I started collecting data at a synchrotron, we'd be talking about doing, you know, on a good day, we're doing 1-2 second images, and then there's a 3-second readout. But now we're doing 55,000 frames in 17 minutes. And I kind of, picking up now, but now over the last year, that's becoming normal. And that's kind of weird, I guess. But it's still quite impressive even when you think about it. But yeah, and I guess the net result was high quality experimental map, so you can see the map after solvent flattening, and a relatively large fraction of the residues were auto built as well, actually, but not sequenced. So that was the next challenge, if you like. So just to finish off, really, kind of talked a little bit about what we have, what the sort of things that we're doing at the Beamline now. And I think from the data that we've collected so far, I think what we've really kind of seen is there's really kind of a clear advantage to, you know, exploiting smaller beams and also being able to change beam sizes rapidly. So that's kind of determining where we're trying to go over the next few years. I-24. So what are we doing about addressing that in the future? So got a schematic of the Beamline. So over the next few years, over the next few months, I mean. So we're going to repolish the first pair of mirrors. So they are due to be sent away at the end of August, and we'll get them back early next year. So that will improve things. And then we're also in the middle of manufacturing a new pair of Microfocus mirrors. And the combination of those two things will mean that instead of 8x8 micron full beam with full flux, we'll have a 2.5 by 5 micron beam with full flux. And then also a more homogeneous defocus beam as well. So hopefully the idea is we'll be able to address even more challenging proteins, more challenging problems. And then coupled to that as well is we're also upgrading the insertion device, so we'll get a superconducting undulator, cryo-cooled, not superconducting, that's still a few years away, CPMU, and that will be hopefully that will be early 2016. So we've got the combination of two things now, so we're going to have a smaller beam size and more flux. And that's really starting to determine the current project that I've been working on quite a lot for most of my time recently, and that's an end station, an upgrade of the end station. So the image shows the current end station. It kind of looks like any standard MX beamline, if you like. Cryostream, just about see fluorescence detector in the background, on-axis microscope, and a sample stage coming to the right. There's a couple of disadvantages that we had. Well, I shouldn't really say disadvantages. It's worked very well for us over the last few years, but it's not really designed for a 2 micron size beam or data collections of more than 100 hertz or fast grid scans, fast line scans. They're kind of really pushing the end station to its limits. Another limitation is we can't switch between in situ and cryo modes automatically. That still requires a member of staff to mess around with stages built on a different stage. So we'd quite like to make that automated to give ourselves a little bit more free time, I guess. So yeah, so so this is the end station upgrade. And what's kind of special about this is the Beamline will have two goniometers. So one horizontal goniometer dedicated to in situ, to tray screening. So the tray gets mounted in the X-ray beam, and the tray will be mounted automatically by the robot. So it will be a tray hotel, the Beamline. And then the second goniometer, see down below here, will automatically move up into the X-ray beam position for pin data collection. So you'll be able to automatically move between room temperature, cryo, and cryo data collection. In both cases, sample exchange will be fully automated. And then other benefits as well. So improved sample viewing, we'll be able to do laser excitation of samples through the on-axis microscope, improve sample positioning. So I did make one mistake actually. I thought I had some nice pictures of the offline construction, but I forgot to put them on my laptop. But offline construction of that is now basically complete, and we're going to start the online construction hopefully in 2 weeks. So in November, this will be in place at the Beamline, ready to be used. So yeah, so quite a lot of exciting developments at 24. Okay, so just to start to summarise. So for room temperature data collection, I think kind of the lesson is that collecting faster allows more data to be collected. Microbeams, powerful, small and large crystals. And really, I think for any microfocus Beamline, say the lesson is that experiments take more care to set up, take more effort to get right, but I think you have to kind of resign, maybe resign is the wrong word, you have to be prepared that that's an aspect of microfocus, but the rewards can be quite large. I didn't mention anything at all about access modes or timing of calls or whatever, so I can answer questions afterwards, but there's details about things like that on the Diamond website if you want to look for stuff like that. So just to finish off, I-24 is a big team of people. Clements, especially Clements, Detectors gave us the loan of the P300K, and then the user examples from Taurus, Oxford, and UEA. So that finish, and yeah, if you've got any questions, I'm happy to try and answer.
You said you're trying to speed up, like, changing the bead size. How long does it currently take to change?
So to go from 10 by 10, say, to 20 by 20 takes about, I would say, maybe 90 seconds, 2 minutes. For users, that is unacceptable. I'm joking. But I think, sorry, yeah, I hope that's not on the recording. That's, I should maybe I should explain in a little bit more depth. But so really, what we want to start to address for changing the beam size more quickly than that is if you imagine if you've got a plate-like crystal and you start to rotate, then the projected size of the crystal changes. Yeah. And so what we want to be able to do is change the beam size rapidly during data collection. And that's something that the mirror upgrade will allow, primarily because at the same time we're upgrading the mirror power supplies as well, which means that we can change the voltages much more quickly on the binaries. So that's really what was hinting at with faster beam size changes.
At the crystallography school that happened recently here in Boston, it was mentioned that in Chicago the typical oscillation range is 0.2 degrees, at the Swiss right source 0.1, and that you are using 0.05 degrees per frame. Why? Is that because you have the fastest Pilatus?
Yeah, I think there's just no penalty associated with collecting a 20th, sorry, a 50th of a degree as opposed to a 10th of a degree. There's no time penalty associated with that. Possibly the only penalty is that you have more images to back up. But at Diamond, we don't delete the images. So currently Diamond has half a petabyte's worth of images and no images will be deleted. So at some point, I'm not exactly sure. After a few months, they get backed up to tape, but they're still accessible if you want to look at the data. I think in general, we would recommend don't do more than always start at 0.1 of a degree and then usually go down. But yeah, I think possibly I think to some extent you kind of run into the law of diminishing returns. So there's a big jump in data quality when you go from 0.2 to 0.1. The jump is less significant when you go from 0.1 to half that. But I guess some of the time you need to take everything you can get. So.
And why did the guys who were collecting LPTD anomalous data collect 720 degrees of it?
So basically, I think the idea was they had a limited amount of time, so it was collect as much as possible, and it's a good strategy. Collect more than you think you need, and then if you don't need it afterwards, then that's great. If you collect 360 degrees and then you don't have beam time for 6 months, and you discover haven't got quite enough, then that's really annoying. So. What they collected the 720, I think they even collected more than that, and they cut back.
From a single crystal?
So I think it was from four crystals.
Oh, so 720 was total oscillation range from the 4?
720 was the total oscillation at each energy.
So
they collected 720 from 4 times 4, so over 4 crystals, at 4 wavelengths.
Because that way they just have more data for the same oscillation range.
Exactly. So particularly for anomalous data, and you can see this like if you see for example, like the Hendrickson papers on the sad phasing. The key thing for anomalous data is multiplicity. At some point, getting the multiplicity up is just making your estimates of I and sigma I more accurate, and it's increasing the multiplicity. And that's kind of really what the approach that Neil has taken is collect as much data as possible at some point, and then afterwards kind of say, I'll cut back. And that was kind of the approach.
And that was then just cutting back, or was it also zero dose extrapolation?
No, there's no zero dose extrapolation.
Right.
So it seems your outrunning damage strategy is limited more by detector read rate than flux, if I understand.
Currently, because we're limited with our current large detector. Yeah, we're limited to 100 hertz.
So what's the outlook on detectors?
What's the outlook on detectors? Oh, there's a how long is a piece of string question. So, well, there's a few different things in the works. So well, how much was somebody to give? Okay, so Detectors have got the next generation detector is called the Eiger detector. I don't know if you're familiar with that, but that essentially has no dead time. So for the Eiger detector, you can read out much faster, so up towards a kilohertz. There's some drawback, and it also has a much smaller pixel size than the Pilatus. So if I remember correctly, I think the pixel size is approximately 70 by 70 in comparison to 172 microns for the Pilatus. So that has some advantages. It also, but the maximum count rate that you can get with the Eiger is slightly lower than the Pilatus. There's also, from PSI Detector Group, there's Jungfrau and Monk detectors. So they're basically working their way through the mountains in Switzerland and they decide what to name their detectors. And then there's also a lot of detectors, well, I don't know if you know, from ADSC in the States, for example. So they have the detector, which I was speaking to Chris Nielsen, he's kind of trying to do it. I don't know whether they got it installed yet or not. It's been installed right about now at NSLS. So they have a fast detector that can counting and integrating modes. So that starts to look quite interesting. And there's a few others as well. But yeah, so even though I think the Pilates kind of changed the game, I think, in detectors as synchrotrons, so that kind of really moved on to continuous data collection, not opening and closing the shutter. But it's still developing rapidly. So yeah, I think over the next 5 years there'll be a lot more changes.
Right, if there are no more questions,